fill it out. Yeah. Some people might have got here late today, so I want to make sure I mark them present for today only. All right, so we are going to begin doing some math, and then we'll take a break at 9:15 for 15 minutes, and then we'll continue, okay? Yeah, there is a lot of stuff that we have to cover. Unfortunately, I was almost crying writing out the syllabus because I have to go so fast sometimes. But again, please ask questions if you have to. So we are going to be talking about, we are not going to be doing calculus yet. The calculus part of the course begins in chapter 2. Chapter 1 is about limits, and we are beginning with section 1.5, which is called the limit of a function. And I haven't taught this course in years, so I don't know the sections here. Yeah, limit of functions. Section 1.5. This course consists of two parts. We have the derivative part, so it's called differential calculus, and then we have the antiderivative part, which is called an integral calculus. The differential calculus has to do with rate of change, how fast things change, okay? So when we differentiate a function, we try to determine how fast that function changes at some point, okay? And to understand all of that, we have to know limits, okay? So what is really a limit? A limit is basically trying to see what happens to a function as x gets close to a certain number. All right, let me show you a picture here. So let's say we have some function. And this function has a certain point of discontinuity. Okay, as you see this function, if I were to draw so what did I do when I drew this function? I drew this segment, and then I had to pick up my pen and then continue at some time later. Okay, so this function has what we call a discontinuity. Okay, we're gonna be studying discontinuities later on, but this function basically has a hole, okay? So if it has a hole, then it is undefined at this point. Let's say this point is A. And let's say that this value, the y value, is L, okay? Now, this function, since it has a hole, then it is undefined at x equal to A. So notice that the function does not exist when x is equal to A. Basically, yeah, x equal to A is not in the domain of the function. X equal to A is not in the domain of f of x. So call this function f of x. Domain excludes A. Okay? Yeah. So it would be wrong to say that f of a is equal to L. There is no y value. There is no y value for when you put a into the function. Okay, see, f of a here does not exist. And it's not equal to L. But yeah. Let me just box that because it's really important. F of a does not exist, so we cannot say f of a is equal to L. This is wrong. F of a doesn't exist, period. So it can't equal to L. All right? But we can somehow describe what happens to the y values as x gets close to a. Okay, we can't say what happens exactly at a, but we can describe the following, that the function approaches L as x approaches a. Okay, so as x values get close to a, you can get close to a from the left of a or from the right of a, it doesn't matter. Okay, but as x gets close to a, see, this is happening. Look at this point. Look at the point on the graph, guys. As x gets close to a, the point is getting, so the y values are getting close to L, right? This is happening. You're getting close to L. It doesn't matter, again, doesn't matter from what side of a you're approaching a, but as we approach a, the y values approach L, okay? That's what's happening. So we can describe this using a limit. So we say limit of f of x as x approaches a is L. Okay? And we can write this statement in notational form. For limits, we call that LIM. LIM stands for limit. So limit of f of x, then we write f of x. And then to indicate x approaching a, you write x below the LIM notation. And then for the word approach, we use an arrow. Let me write that in green. So x approaches a. Yeah, so again, limit of f of x as x approaches a is equal to L. Okay, that's how you write that statement. Okay, so although the function doesn't exist at a, but its limit does exist. The limit of a function is not the same as the value of the function. Again, it's just telling you what's happening to the y values as you're getting close to as x is getting close to a certain number. Okay, y values are getting close to L. We are not exactly right on L, but we are around L. All right? Yeah, let me show you an example here. I can do this on GeoGebra. I was playing around with GeoGebra last night. Let's look at a very interesting function. F of x equal to, let me see, sine of x divided by x. Okay, so this is a graph of this function. The sine function is a wave function. And when you divide it by x, since the denominator x gets bigger, then the whole thing gets smaller. So the wave is kind of like getting killed. As x gets big, the wave gets shorter and shorter. Is what's going on. Now, we don't need to be able to graph this function, but let's just look at the function for a moment. Okay, this function, sine of x over x, is undefined. When x is 0, the function is undefined. Do you all agree? The denominator of this function becomes 0, so the function is undefined when x is 0. Division by 0 is not allowed, okay? Obviously undefined. But we want to know what happens to the function as we get closer to 0. Okay, so I'm going to ask GeoGebra to do a table of values. Let's go from -1 to 0. And I'll just go by increments of 0.01. Okay, so we have two columns here. We have the first column. Give me a second, let me see if I can annotate here. See if this works. Yeah, so we have the first column. The first column are x values. And then the second column is the value of the function. Okay, so for instance, when x is -1, the value of y is 0.84. Second column, second row, when x is -0.99, the value of y is 0.8447, so on. If you pay attention to these x's, they are getting closer to 0. Y'all see that? Yeah, 0.57, 0.56, -0.55, -0.54, -0.53. They're getting closer to 0. Okay? I want you to pay attention to the y values. So let's just start from the beginning. Okay? So the first y value was what? 0.841. And then again, pay attention to all of these y values and see what they're getting close to. What do you guys think? What do they get close to? Anyone?
1.
Yes, they're getting close to 1. Okay? But when, again, as x goes towards 0, the y values get close to 1. But look at what happens at 0. There's like what the F for y. There's a question mark. Okay, I call that what the F, the question mark. What happened at 0? The function becomes undefined. Okay? F of 0 does not exist. Okay, but around 0, so we are right here around 0. The values of y are around 1. Okay? When x is around 0, y is around 1. Although y is undefined when x is 0. Okay, so let me write about this. For example, f of x equal to sine of x over x. Okay, so note that again, the domain of this function is anything but 0. Domain is the set of x values such that x can't equal 0. Okay, which means that again, f of 0 does not exist. D&E does not exist. All right, so we observe now. Mathematically, we'll prove why the limit is 1, but numerically we saw that so we observed. I'll just write it down. We observed that as x approaches 0, y value, y approaches 1. Okay, so here we write down limit as x goes to 0 of sine of x over x is equal to 1. Although f of 0 is not defined. So again, if I write down what happened, if I summarize what happened around or when x is around 0, y is around 1, although there is no y value. At exactly at 0. Okay? So, an example. Let's look at another example. Any questions so far on this, guys? So this is you could do this on Excel if you want to. You can, I can show you on Excel if you want, but you could also do it on GeoGebra. Let me type the name, GeoGebra, in the chat box. It's a really cool utility. It does a lot of cool stuff, okay? But let's look at another example quickly. An example where the function is undefined, but the limit is not undefined. So say we have f of x equal to x squared minus 1 divided by x minus 1. Okay, so at what point, guys, is this function undefined? Anybody?
1.
Exactly. 1 makes this undefined. A rational function is always undefined when the denominator is 0. Okay, so here, again, domain is a set of x values such that x can't equal to 1. Okay? Yeah. What does this mean again? This means that f of 1 does not exist. Okay? So let's plug the function in GeoGebra and see what happens when x does get close to 1. Maybe something good will happen. Okay, so we have x squared minus 1. Oh, it closed the parentheses. Let me fix that. X squared minus 1 over x minus 1. Okay. The graph of this function, so let me show you the graph later, okay? But let's ask for a table of values. So I have to edit this. So let's say we go from -2 to 1. Okay, again, wait, from 0 to 1, that's better. Yeah. So since 1 is a bad point, I want to know what happens around 1. So I define around 1 from 0 to 1. You can define it from 0.5 to 1. It doesn't matter. So I'm just going to get close to 1 by increments of, like, let's say 0.1. Let's see what happens. Okay, so table of values. Here we have when x is 0, the value of function is 1. So what do? You just basically plug 1 into the function, right? Just plugging values into the function. So if I plug 0 here, I get -1 over 1, which is equal to 1. Okay, again, this is just a table of values. Okay, and we are getting close to 1. Let's see what happens. Pay attention to the y values, to those, I messed up, to the y values here. Okay, so we have 0.29, 1.29, 0.3, 1.3. When x is 0.31, y is 1.31. But as we are getting close to 1, the y values seem to be closing to 2. Okay? So when x is 0.99, y is 1.99. But when x is 1, the calculator is like, what the F? Right? It's undefined question mark. But look at that. These are getting closer to 2. Okay? And we call 2 the limit of the function. Okay? But I want you to look at the graph, guys. Look at the graph. This is the graph. Okay, the graph is a line. Now, this line has what we call a discontinuity, okay, at 1. At 1, things are undefined. So if you were to graph this function, there would be a hole right at 1. Okay? That's what the graph would have looked like. But let me write down what we just observed. So here we observation is that as x gets close, or as x approaches 1, y gets close to 2. All right, so again, we write this using limit notation. Limit as x gets close to 1 of the function, which is x squared minus 1 over x minus 1, is equal to 2. Okay, I will be showing you how to evaluate these limits mathematically, like using algebra, but we are doing this right now only numerically. Okay, not algebraically, but numerically. Okay, Randy, what's the question? Why is the thicker there? Which thicker? It was probably a part of the table. Okay, so again, I am not able to take 1 and stick it into the function because I get division by 0 and that's undefined, but around, when x is around 1, y is around 2. Around 2. Although there is no y value exactly at or exactly when x is 1. Question? Any questions?
Professor, the limitation is always affect the domain, not the range, yes?
Right, yeah. So limits are a way to describe what happens near a point, not at the point. The value of a function and limit are very different things, okay? A limit is used to describe what happens to a function near a point, not at a point. Let me write this down and we'll take a break. What happens to a function near an x value? Okay, and not at that x value. All right. Okay, so let's take a 15-minute break. Let's come back at 9:33. Guys, go ahead and take a break. Anyone who still has difficulties with the limit notation, if you do, please ask me. Again, this stuff is not calculus, okay? This is just the language of limits that we are learning. We're not yet learning the actual calculus. Oh, there you go. So yeah, I was saying, if you have a question, please let me know about limits, limit notation. Yes, I can explain the notation I use for the domain. Absolutely. Yeah, so this this reads as the set. So when I open braces, that means set. Set of x's, I'll write it down. And then the bar here means such that. So set of all x values. The bar means such that x can't equal to 1. X is not 1. This is called the set builder notation. You can also use the interval notation by saying that x runs from -infinity to 1, parenthesis, at 1 means we're excluding 1, union from 1 to infinity. So yeah, parenthesizing 1 means 1 is out. It's excluded. Yeah, so again, limit in most cases, in all cases that we saw, exists, although the function doesn't exist. So let me draw all cases for a limit of a function. And we shall discuss continuity later on, but I'm going to mention continuity. Questions?
Wait, can you bring it back up again a little bit just to finish writing that down? Thank you.
Absolutely. So here Jose is asking, Jose, you can make that, if you guys have a math question, you can make that public, guys. Math questions, public, chatting, not public, just no chatting during class. But Jose, you can make that question public if you want. So Jose is asking, what would you write if you also wanted to specify x can be any real number except 1? Well, this tells you that. This tells you you can, so if you wanna, Jose, if you wanted to write exactly as what you just said, that would be this, which is kind of redundant. So you can say x is such that x is any real number. Okay, that notation says x is, so that E means is in the real set with x can't equal to 1. This is a redundant notation. It's redundant. So this by default says that x, when you say x such that x is not equal to 1, this means x is anything but 1. All right, anything else is redundant. So I'm just gonna take that out, Jose. Yes, Jose, the real number part is implied. Yeah, absolutely. Okay, so let's look at all cases for a limit and types of functions. So here we have a function. Look at this graph, guys. This graph, y equal to f of x, is said to be continuous. This graph has no holes. It doesn't act funny, okay? We call this a continuous graph. You don't see a hole, you don't see a vertical asymptote, you don't see jumps. We're gonna be dealing with all that, but just a typical nice smooth function. Let's say that here is A and this is L. So for this function, f of A exists. F of A is L. Again, if there was a hole here, then f of A wouldn't exist. I will draw that for you. But here, f of A is equal to L, right? But at the same time, when x gets close to A, y gets close to L, okay? When x is around A, y is around L. The limit is also L. The limit as x goes to A of f of x is also equal to L, okay? So this is one of those cases where both the function and the limit exist at A, okay? We call this continuous. This is a continuous function. And then we have the case where the function has a point of discontinuity like that. So again, let's say this is A, and that point, the y value at that point would have been L. So here, as we see, f of A does not exist, okay? But the limit here is L. Limit as x goes to A of f of x is equal to L. So again, this relates to the examples that we have been looking at. Okay, so again, at A, f does not exist, but around A, f becomes around L. Okay, and then we have functions that do exist. So again, this has a hole at A, but with certain functions, imagine you take out a point, you remove a point, and you put it somewhere else. So imagine I take that point out and put it like here, okay? This type of discontinuity is called a removable discontinuity. We'll study this in section 1.7 or 1.8, I think 1.8. But here again, the limit is L, but the value of function is something else. I don't know, what do you want to call that? Call that y value, call that, let's see, B. Let's call that B. So notice here that f of A is equal to B. It exists, okay? But the limit of f of x as x goes to A here is equal to L. Okay, so here the function has a different value than the limit at A. This can happen. This is what we call a piecewise function. That's what this is, a piecewise function. Okay, so for certain x values, we have a certain function, and then for this certain x value, we have a different value. We have a specific value for the function, but this can happen. Again, this is a piecewise function, okay? Yeah. Any questions? So, I mean, just look at the graph for all of these. So for all of these graphs, when x is around A, y is around L, okay? We are getting close to L as x gets close to A for all of them. Okay? All of them have the same y neighborhood. Yeah. Yeah, again, we're gonna be studying discontinuities in section 1.8, but this is called a removable discontinuity. This is also a removable discontinuity, and then this is continuous. Okay. So, yeah, let me see here. Yeah, so let me show you an example of maybe this scenario. Let's say f of x is equal to x squared minus 1 over x minus 1. I'm defining here, guys, I am defining a piecewise function, okay? So we have that top function, and this piece is defined when x is not equal to 1. Obviously here x can't be 1. Okay, so that's that piece. And let's just say that the value of y is negative, or actually let's make it 3 when x is equal to 1. Okay, again, this is a piecewise function. Okay, now before I proceed with graphing this function, let's simplify this function. Okay, that top piece, this piece, can be simplified because the top is factorable, and we can cancel out a like factor. So note that here, x squared minus 1 over x minus 1 can be written as, so the top x squared minus 1 is a difference of squares that factors to x plus 1 times x minus 1, and the bottom is just x minus 1. And here we can cancel those x minus 1 to reduce that piece to x plus 1 only. Okay, so this rational function, y'all know what a rational function is. A rational function is when you have a division of two polynomials. Okay, this rational function reduces into a polynomial. Okay, so we can rewrite f of x as f of x equal to, okay, so that x squared minus 1 over x plus 1 is now, let me actually color code these, so that this top piece, let's do that in green, and the bottom piece, let's do that in blue. Okay, so the green piece is now just x plus 1. Okay, so this x plus 1 is defined for all x's except for when x is 1. Okay, and then for when x is 1, the value of y is just 3. Okay, a piecewise function, easy as hell to draw. Okay, this is just a line, and this is just a single point in space. So let's draw. Okay, so to draw the line, you can use the slope, intercept, you can pick points, whatever you want. So for instance, if I put 0 into this piece, the value of y is 1. Okay, so let's say this is 1, 2, 3. Yeah, at 0 it's a 1. Okay. And you can pick another point into that line to choose a second point on a line. You could pick a 1 and plug here, but we know that the function is not defined at 1, so there shall be a hole. Okay, so if I plug 1 here, I get 2. But then there's gonna be a hole right there. So 1, 2 is a hole, like that. All right, and then again, the graph is a 9. Let me exclude that hole. There we go. So this is the green piece of the graph, and it goes forever like that. Okay? Now again, when x is 1 itself, the value of y is 3. So that's just the point 1, 3, which would be right here. Okay, so this is the graph of f of x. Okay? So let's look at the limit, or let's look at a value of f at 1. Here, f of 1, what is it, guys? F of 1 is
3.
3. But what about the limit? Limit of the function as x gets close to 1.
2, right?
True.
2.
It's true.
Very good. Just look at the graph. This is really no math. You're just looking at the graph. That's all you're doing. We are not solving these mathematically yet. We are just looking at them graphically. But here is 1. Okay, so as x gets close to 1, now there are 2 ways that you can get close to 1. You can get close to 1 from the left or from the right. Now it doesn't really matter. As x gets close to 1, okay, just imagine you are walking on this graph. Okay, and horizontally you're walking towards 1. As you walk towards 1, you are going, of course, upward. Your y values are getting close to 2. Okay, and again, from the left, if you're horizontally approaching 1, your y value is approaching 2. Okay? So here the limit is 2. All right, and that's it. But yeah, this is how you calculate the value of f at 1 and the limit at 1. Okay, any questions? All right, let's just do one more problem. Let's say we have g of x defined as let's see, what would be a good problem? All right, so let's go with the same, maybe with the same function. Let me see. Or maybe I can go with the graph of 1 over x. Yeah, let's just do that. So let's say g of x is 1 over x when x is not equal to 2. Okay. Now I'm hoping that you guys know the graph of 1 over x. So Randy, I know you are so excited and you wanna talk about discontinuities, but let's just hold on to that for now. I just want to go over the basics. Okay, and
Is 0 or is 2 excluding?
yeah, of course, the domain of this function excludes 0. You're absolutely right. Okay, but I want to also exclude 2 from this domain. Okay, I just purposely chose to exclude 2 from the domain. Just wait until I graph that and you'll see what's going on. Yeah, so the graph of 1 over x, hopefully you'll know how to graph that. It's the reciprocal function. It has asymptotes. Okay, now, of course, again, as Haida said the domain of this function excludes 0. But I also want to take 2 out of the domain of this graph. Okay? And let's just say that x is equal, g of x is equal to 1 when x is equal to 2 itself. Okay? So let's graph this function. This function is already as simple as it can get. But let's just quickly look at the graph of 1 over x. Again, you all should know what that graph is like, but let me graph it just quickly. So this is the graph of 1 over x. It's a hyperbola. It has 2 branches, and everyone should be familiar with it again. It has vertical asymptotes at 0. So right there, we have a vertical asymptote. Here we have a vertical, of course, vertical asymptote at 0. The function goes to infinities because you are dividing by 0. Dividing by really small generates really big, okay? And it also has a horizontal asymptote right there. Asymptotes act as boundaries, okay? Because when x gets big, y gets small, okay? But yeah, this is the universal look of the graph. But again, everyone should know about this graph already, okay? It's called a reciprocal graph. Okay, so as you see, the domain of this function excludes 0, fine, because there's a vertical asymptote there. But from the graph, from the green graph, I am again excluding 2. So if I graph the function, again, here is 2. This is what the function looks like. And again, there's a hole over here because 2 is out. Okay, now, if I were to put 2 into the function, what do I get? I get 1/2, right? It would have been 1/2 if the point was actually there. So what I'm doing is I am removing that point to 1/2 and putting it somewhere else. I'm putting it at 1, right here. Okay? Now, why did I do that? I don't know, I'm crazy, I guess. It's just the way this function is defined. What can I say? It's just a definition of the function. That's all. There's no reason that I did that, but we're just doing for the purposes of finding limits. Okay, but again, guys, what is the value of g at 1? At 2, sorry, at 2. What is g at 2?
1.5.
It's 1.
G at 2 is 1. The definition says that, right? When x is 2, g is 1. Okay? But when you look at the limit of g of x as x goes to 2, what is that limit equal to?
Half.
Half. Yes. So in the neighborhood of 2, the value of the function is around half. Okay. Yeah, so again, as x is getting close to 2, y values are getting close to half. All right. Again. And yeah, I am not yet talking about what's happening around 0. We'll talk about that later today, but okay. So let's now talk about one-sided limits. Yeah, and if you notice, I was earlier talking about x getting close to, for instance, 2 from either right or left, okay? Sometimes when you find limits from sides of a function, those limits might not be the same. The function might jump. When a function jumps, you end up with different sided limits. Okay, so let's talk about that. Yeah. There's really, again, these are all notations, okay, that we are learning about. Barely any math, but let's say we have a function with what we call a jump discontinuity. So again, this is a piecewise function, like that. It consists of 2 pieces on different domains. Okay, so let's say things are changing here at A. Okay, we have the left-sided limit. The left-sided limit is when x is getting close to A from the left. Okay, that's the left, and the right-sided limit is when x gets close to A from the right of A. So how do we write those limits down? Now, imagine that from the left, we have L1, and from the right, we have a different y value. Let's say here the y value is L2. L1 and L2 are not the same, obviously, because of that jump. Okay, so here we write down limit. LIM, limit of f of x, let's say the function is f of x, as, maybe I could write that in blue. No, let's just keep it. Limit of f of x as x goes to A. Now, how do you write left in math? We use a superscript with A, for A, using the negative notation. So that's written like that. That reads as x going to A from the left. Okay? Now, that negative notation is not a quantity. It doesn't really mean negative. It means left. Okay? Just make sure you understand that. So this limit is equal to L1. Again, this is the limit of f of x as x approaches A from the left. And the value is L1.
Wait, so this limit doesn't exist because they don't match up, right?
Yeah, well, so we'll talk about the existence of the limit itself. Yeah, just give me a second. And then we have the limit of f of x as x approaches A, but from the right, which you use a positive superscript. Now, look at the graph. Imagine you are walking on this graph, okay? And you are on the right of A. Here is A, you are on the right of A. You would be on the blue piece, walking on the graph. As you walk, you're getting you're vertically getting close to L2. That's what it is, L2. That limit is L2. Okay, but again, we read this as the limit of f of x as x approaches A from the right. So when you see a superscript, negative or positive, those are one-sided limits, okay? When you don't see the superscript, it means both sides, okay? But that's what it means for now, all right? So, what about the limit as x goes to a of f of x? Again, this means from both sides. So this is the limit of f of x as x approaches a from either side. That's what it is. Okay, yeah, the superscript plus minus means from both sides. And in this case, for this graph, as who was it, Randy or Angel? This limit doesn't exist. This doesn't exist because we don't get to a specific value from either side. Whenever the jump happens, the limit of f of x does not exist, okay? Although the one-sided limits do exist, but what am I gonna say? What would be the answer to this? You can't have two different answers for the same question. So this thing, according to this picture, does not exist. All right, so this is very, very important. And I don't know if they call it a theorem, but yeah, they do. It's a theorem. So we'll say that the limit as x goes to a of f of x is equal to L if and only if. This is a two-way statement. If and only if. If and only if is a two-way statement. You can switch the conclusion and the hypothesis, the theorem is still true. So if and only if the limit as x goes to a from the left of f of x is equal to L, and, okay? Not or. And the limit as x goes to a from the right of f of, from the right is also L. Okay, both of those limits must be L in order for us to say that the limit is L. Okay, so what does this mean? This means that if the limit as x goes to a from the left of the function is not equal to the limit of the function as x goes to a from the right, maybe. Yeah, if the left-handed limit and the right-handed limit are not the same, then the limit doesn't exist. The limit at A does not exist. So in order for the limit to exist, the double-sided limits must be equal. It is common sense, guys. Does that make sense? And that's what's happening with that graph. You're getting two different limits. Make sense? Excellent. Okay, so let's do a problem. Let's do a non-mathematical problem, non-algebraic problem. there are a bunch of problems in the book where you just look at the graph and and give the answer. Okay, so I have some pictures that I got this picture from Reddit last night. It's kind of cool. Let's do that maybe here. Yeah, that's good.
Here's something I found from ShareCare.
Alexa,
There are
stop.
plenty.
Did I say Alexa? Hey, no, stop. Okay. All right. And I want you guys to help me out on this, okay? So I will be asking you guys questions. And again, there's no math, okay? It's you looking at a picture. That is all. Maybe let's just go to the next page, make sure I have enough room. Okay, good. All right. Let's go with -4, okay? So, and let's say this is some function f of x. I will write the question and I want answers from you guys. So limit as x goes to -4 from the left, okay, of the function. So again, do not confuse the indicator with a sign. Okay, this is not a sign. That is an indication. Okay, this doesn't have a sense of value attached to it. This does. This is -4. Okay, this reads as the left of -4. All right, so let me get you started here. Here's the function. Here's -4, okay? That is -4. Imagine you are walking on the function, so on the left of -4. So here's the function. I am on the function from the left. What do I get close to? What does my y value get close to?
3.
3. 3. Okay? Look at that. As I go up, okay, I am gonna be on the 3rd floor. Okay, so the limit here is 3. All right, so that's that. Limit as x goes to -4 from now the right. Again, let me color code these. So that's
Wait, stupid-ish question, but wouldn't you be walking down from the point? So wouldn't you be going like downward since it's going to the left?
got you. That's not a good question. See, that's a good question because that could be a reason that some people are confused. And if you never asked me that question, if you didn't ask me that question, I would have not known that people think like that. So thank you. I bet there are a lot of people who think like that. We always, look, what does this say? Look at that. Look at what this says. This says x is approaching -4. So if you are going away from -4, then that is a contradiction, right? This is -4. We want to get close to it from the left. So here again, here we are. If I go this way, if I go that way, I'm going away from -4, but I want to get close to -4 on the left. So that's what's happening. We are getting close to -4. That's what this arrow says. Get close to -4 from, so here's the left of here's the left of -4. So we are on this side of -4 on the function, but we are getting close to it.
Okay, that makes a lot more sense.
Yeah, and then this one, so who wants to, let me go with Louis. Louis, welcome back, man. Can you tell me the answer to this question, Louis? Waiting for Louis.
It's hard to tell.
Oh, well, let's help you out. So here's -4, and this says from the right. Okay, so -4. On the right of -4, you're gonna be on this piece. Okay, I'm gonna be on this piece. And I wanna get close to -4, so what point do I get close to?
+4?
Is that yes? Yep. As, yeah. So here we are on the left of -4. Okay, you are walking horizontally towards -4. You are gonna be going up, getting close to that point that has a y value of exactly 4. Yeah, this y value here is 4, so that limit here is 4. Okay? So again, we're going up, getting close to that point. All right? So now, what about the limit at 4? Limit as x goes to 4 of f of x. What is this? Let's go with Nathaniel. Nathan?
Yeah, I'm here. So as x is approaching 4 from the left, it is -3.
Oh, I'm sorry. That I meant to say -4 here.
Oh, -4. It does not exist.
Does not exist. Very good. E. Because the limits are not the same. They're not the same. If these were the same, then this limit would have been that, but it's not. Okay? Now, what about f of -4 itself? This is not a limit anymore. This goes back to algebra 1. Let's go with Noah. Noah, can you tell me what is the value of the function when x is -4?
It would be 3, right? Because it's defined at,
Very good.
yeah.
Exactly. So if you look at the function, the graph, at -4, there's a hole here, which means that this is not going to give you the value of f, and this is not a hole. This is included, and here the y value is 3. Very good. So this function is defined at -4. Now, in the case where this was a hole, if this was a hole also, f of -4 would not exist. Okay, so that's that. Let's talk about -1. So limit as x goes to -1. Let's go from the left. And does Randy want to go with this one? So here is -1, and this is the left of -1. What y value do I get close to? Randy.
2.
You're Randy? 2. Randy, you sound like a girl. What happened?
Oh man.
Randy, you sounded like a guy to me a couple of days ago in my pre-calc. What happened? Oh, it wasn't Randy. Okay, it wasn't Randy. I got you. All right. Okay, so I'm just joking, Randy. I sound like a girl sometimes. It's okay. My voice cracks sometimes. But yeah, the limit here is 2. So here is -1. Get close to 2. And then what about the right side of limit? So limit,
It's 2 again.
yes, from the right for the function that's also equal to 2. They both end up in the same neighborhood. I'll be using that word a lot. Same neighborhood. Okay? So that's also 2. So now what about the limit as x goes to 2? Let's go with Rosa. Rosa? Hi, Rosa.
Hi.
Hi. What about the limit at 2?
2.
Yep. Yes. And that's what the rule says. The rule says if both limits are L, then the limit at A is L. Okay?
Oh, Professor,
Yeah.
I think you should have wrote like x as x approaches
Negative
-1.
1.
Yeah, you're right. Thank you. -1. Thank you for that correction. That's -1. And Rosa, can you also tell me what is f of -1 itself? Rosa.
I think that will be 1.
Yes, very good. This is called a removable discontinuity, which we'll cover later. But the point has been removed from the graph and it's put somewhere else. So it has a different y value. But exactly, right there, the value of the function is 1. Excellent. Okay, now let's talk about maybe a different limit here. So the next one is actually obvious, but we'll just write it down. Limit as x goes to 4 from the left for f of x. Let me go with Saad. Saad here is 4, and we are approaching 4 from the left of 4. So what does y get close to, Saad?
-3.
-3, excellent, right there. You are going down imagine you're taking escalators down, you're getting close to, you're going to the 3 floors below. Okay, so that is a -3. Limit as x goes to 4 from the right for f of x. Let's go with Susie.
-2.
Excellent, -2. Here's 4, and we are on the right of 4, getting close to, we're getting close to -2. Excellent. And then, Susie, what about the limit of f of x when x goes to 4?
-2 also.
Just think about it. So this is not a cited limit.
Oh, just kidding. Sorry, does not exist.
Does not exist. Yeah, they are different. These are different values, so this does not exist. So when we say DNE, guys, please pay attention with the equality. Don't say equal to DNE. We use equality when we compare two values, or when we assign a value to something, to a variable. That's when the equality sign is used. So how can something equal to something that doesn't exist? It doesn't make sense. So this is just a statement. This limit does not exist. When you say it's equal to DNE, you understand what I'm saying? It's just nonsense. Okay, so just say it doesn't exist. Look at that. I'm not using equal DNE. Okay, so what about f of 4? And let's go this time with us. Let's go with, who did I miss here? Kevin.
Yeah.
Hi, Kevin. What about f of 4?
would be -2.
Excellent. Yeah, right there. So this whole doesn't count, but it's, yeah, -2. Very good. And that's it. Okay? Yeah, so if you understood what's going on here, then you definitely understand limits.
Professor, I didn't understand when we say when x approach to 4 from the left, the f of x is equal -3. So when we have a whole here, why we included the same as the amount of this function actually?
So here, right, all right. So here's 4, and you're on the left of 4. The y value is getting close to -3. It doesn't become exactly -3. It is getting close.
So why we put equal?
Because this is a limit. The limit is -2. The limit is -3. We don't say f is -3. We say the limit.
Oh, thank you.
Yeah. All right, excellent. Thank you, Burkhan, for answering those questions, messaging me privately, but let's see here. So what about doing things algebraically? We have about what, like 15, 20 minutes? Let's look at a problem where we have to do things algebraically, okay? So this would be, I don't know, I'll just make something up, okay? So imagine that you are given a function instead of a graph, a piecewise function. Let's say f of x is equal to, and you really don't have to actually graph these. Oh, wait a minute, can we yet do these? No, we can't. We can't do this because I haven't gone over limit laws. Give me a second, guys. Yeah. All right. Okay, so next I want to talk about vertical asymptotes. So imagine that you have a graph that has a vertical asymptote. Like, how do we describe what happens near that vertical asymptote? Okay, so I'm just gonna draw some function that has a vertical asymptote. And again, let's just say that this function has a vertical asymptote at x equal to a. Okay, that's x equal to a. And let's just say that the function does this. And then here, it does that. Okay, this function is, we say it blows up. It goes to all the way up to infinity from the left, and on the right of a, it's going down to -infinity. Yeah, this goes to -infinity, and here it's going towards +infinity. So how do we describe the behavior of this function near that red line? That red line is acting like a wall, okay? WA LL, a wall. So here we say that the limit as x goes to a from the left for the function is equal to positive infinity. Obviously, if you are on the left of a, walking towards a, you're gonna be hitting that wall. So if you have to keep walking, you're gonna be walking up forever. Okay, this will go up forever, so the limit is infinity. And if you are on the right of a, walking towards a, we are always walking towards a. That's negative infinity. Okay? When the limit of a function is equal infinity, we know there is a vertical asymptote. Okay? Vertical asymptote is when a limit is equal infinity or negative infinity. Sometimes we have functions that go to the same infinity. For instance, again, let's just say that we have, again, let's just say this vertical line is at x equal to a. But this could happen. This is a positive function. So the limit is always positive, but limit of f of x as x goes to a from the left is also infinity. Okay, so again, this is going up to infinity. From the right, it's also infinity. With these limits, by the way, don't exist. Limit doesn't exist in these cases. If infinity, guys, is a non-existing thing, infinity is not a number. So limit doesn't exist. For this situation, though, you can say, you can combine these two statements and say that the limit as x goes to a is just equal to infinity. Since they are both going to infinity, then you could just say limit is infinity. But when limit is infinity, either case, it doesn't exist. Okay? A question from Jose says, okay, yeah, great question, guys. If you read Jose's question, that is a great question. He says, is saying that a limit tends to infinity the same as saying it doesn't exist? What do you guys think? Yeah, why not? So limit,
Go ahead.
if a limit goes to, if a limit doesn't exist, it doesn't mean that it is infinity. If a limit doesn't exist, it could be that you have two different finite limits from either side, from the sides. That doesn't, that means it doesn't exist. Or if a limit doesn't exist, it means that it's going to infinities. Okay, but if a limit does not exist, it doesn't mean it is infinity. It means that there's a jump. There could be a jump going on, but in either case, the limit doesn't exist. So here is the other scenario where we have a vertical asymptote.
So if a limit is approaching, if it goes to like negative infinity from the left and the right, then it does exist. The same thing.
It doesn't exist. It does.
I mean, the limit is in itself
In,
negative infinity.
right. Yeah. Yeah. But we still say it doesn't exist because infinity is not a number.
Okay.
I'll write down what you just said.
But you don't put DNA, do you? You still put negative
Yes.
infinity.
But, well, okay. So still DNE
I mean DNA.
because infinity is not a number. So here limit is still limit as x goes to a of f of x. Here it doesn't exist either.
But how come you put infinity on the second one?
Because for from both ends it goes to infinity, but still infinity is not a number, so we say it doesn't exist. Yeah?
Hold on, the limit exists, but there's no value. But it doesn't. The limit.
No, the limit doesn't exist. The limit doesn't exist.
All right. So do you want us to put DNE or you want us to put the actual infinity?
Both.
Okay.
Yeah. I'll explain what he's saying. Give me a second, guys. Just hang on a second, because this could be a little confusing. So with this scenario, if someone asks you, please listen, guys. If someone asks you, hey, what is the limit as x goes to a? There is no answer. I can't write down what happens here because you're getting different infinities. So here you just say it doesn't exist. That's it. But with this situation, since both limits are infinity, then you can write the limit of f of x as infinity, but still infinity is non-existent. So here we still say it doesn't exist. But this DNE is more specific. It's just infinity, DNE. You know what I mean? Here you could just, you could be more specific and say it's infinity. But infinity doesn't mean it exists. It's still a DNE. This is a specific DNE. It's an infinity DNE. Okay?
So what is meant by infinity is actually that the y value is increasing, right? So what you mean in the second example is that since as you approach a from both sides, the function is what we mean by 10 to infinity is that it's increasing indefinitely. So you can the reason why you still write limit of f of x as it approaches a is because from both sides the function increases indefinitely. So you wish to say that the function increases indefinitely, but yet no limit exists because the function doesn't approach a defined value.
Right, exactly. Yeah, and by the way, the function is not increasing both ways. Here the function is increasing. Let me show you. Here the function is, the function here is increasing. Here actually the function is decreasing. So, but what you meant to say is the function blows up on both ends. It blows up. Yeah. This is just being more specific in saying that when you are getting close to a, from either side, the function goes up to infinity, but still this doesn't mean that the limit exists. Okay, here again, here I can't say this is equal to infinity or negative infinity because we're getting two different infinities. But what you said is pretty correct. So here the function is going down to negative infinity from both sides of a. And since from both sides of a, the function goes down to negative infinity, then we can be specific and say that the limit as x goes to a of the function is just negative infinity. But still, since negative infinity is not a number, we say the limit does not exist. Okay? Anytime the limit is infinity, it's a DNE.
have a question.
Yes.
Is we actually don't care about what the number is, like we don't care about the value in itself. We're just worried about what it is approaching. I feel like just writing infinity or negative infinity justifies like the limit or the value of the limit.
Justifies, yeah. It's infinity is not a value. We don't use the word value. We are just being, again, as I said, we are being more specific with it. It's just that here I couldn't write down this is equal to either infinity because there are different infinities. But regardless, whenever there's a vertical asymptote, the limit doesn't exist. Okay, so let's look at a different question here. Let me put that over here. So today was mostly about analyzing graphs, basically using limits. But here we have the limit as x goes to 4, negative 4 actually, from the left. So here is negative 4. Obviously, there's a vertical asymptote here. Vertical asymptotes are not a part of a graph. So if you ask a computer algebra system to graph a function with vertical asymptotes, it doesn't graph the vertical asymptotes itself. But here's negative 4, and that's the asymptote. Function is, again, going up to infinity. Okay? It's going up to infinity from both sides of negative 4. So I'm just gonna write down infinity for both. And here, if someone asks you, hey man, what is the limit as x goes to negative 4? You can say infinity, okay? And you can also say it doesn't exist. If these were actual finite quantities, like this, if this was a 5 and this was a 5, then this would have been a 5 and you would say it exists. Okay, but infinity is not a number. Okay, let's look at the limit at 1. Limit as x goes to 1 from the left. Limit of the function as x goes to 1 from the right. Okay, so yeah, here is the vertical asymptote. On the left of 1, this is the piece of the graph that's on the left, and it's going up to infinity. So from the left, the function goes up. And from the right of 1, the function is going down to negative infinity. Okay, so if someone asks you, hey, what is the limit as x goes to 1 of f of x, what do I say, guys?
It's infinity, but it doesn't exist.
Because it's not the same.
Yeah, we cannot describe this dne. It's just a dne. Okay, I can't say it's an infinity or negative infinity because they're not the same infinities. You just say dne right here. Okay, and then let's look at the limit finally at 5.
A quick question.
Yes.
If let's say this was on the test and it's one of the ones that where both sides approach positive infinity, and you're asking for the limit for it, do you want us to say infinity and this does not exist, or will either answer suffice?
Yeah, I would like to be specific. So you say, yeah, if the limits are the same infinity, just please go ahead and say infinity as well as the n.
Gotcha.
And if they mismatch, just say the n. Okay? Yeah. Did Arena have a question? I saw her hand. Where did she go? You're good? Okay, very good. So at 5, the limit, the function is just going down forever. Okay, so from both ends, from both sides of 5, the function is going down to infinity, negative infinity. Okay, and since from both sides function goes to negative infinity, then you can say that the limit as x goes to 5 of this function is just negative infinity. And of course, such limit does not exist. Okay? But as you see, all of them are DNE, all of them. These are all DNE. These are all DNE. Infinite limit is just DNE. So how do you do this algebraically? All right, let me just, for the sake of doing homework, let me show you an example quickly. I will discuss this in more details tomorrow, but like imagine I have a function like f of x equal to x plus 1 over x minus 5. This is one of the homework problems, okay? Yeah, so notice, guys, that this function is undefined when x is equal to 5. X here can't equal to 5. That's out of the domain, okay? So just think about it from a numerical perspective. Of course, we can't plug 5 into this function. We get division by 0, and that's all messed up. But the basic logic is that when x is close to 5, the denominator will be really small. When x is near 5, the denominator becomes small. And when you divide by small, the result is gonna be big. Okay? So to answer this question, you can try and graph. Try to graph the function near 5. You don't have to do the entire graph. Of course, that's a little bit complex. But y'all know the sign analysis, right? We all do know the sign analysis. This question shouldn't take more than a minute to answer. So if you look at the sign analysis, you would have to look at the zeros of the top and the bottom, okay? Zeros of the top is x equal to -1, and the 0 of the bottom is x equal to 5. Remember sign analysis? And then you just put those zeros on the number line, -1 and 5, and then you take a test point to see, to determine the sign of these factors. Okay, so for instance, I can here test -2. Okay, -2 makes that factor negative, makes this factor negative, right? -2 plus 1 is negative, -2 minus 5 is negative. And then you have a negative divided by a negative, the result is positive. Okay, the function is positive. And then you could test, for instance, 0. Okay, 0 on x in x plus 1, that's a positive. In x minus 5, that's a negative. Positive divided by negative is negative. And then you can test 6. Okay, both factors are positive. When you plug 6 in, positive divided by positive is positive. The function is positive. Okay? the sign here tell you about, and you can use multiplicities. You know, if you have a shortcut for doing a sign analysis, use it. But these signs tell you which infinity the function is gonna go to, if it's a positive infinity or if it's a negative infinity. Whenever the denominator of a rational function is 0, function has a vertical asymptote. So this is the location for a vertical asymptote. So note that f of x has a vertical asymptote at x equal. I just need 1 more minute, guys. I'm so sorry, I'm keeping it. I will give you guys extra. I will let you guys go 5 minutes, 10 minutes early tomorrow. I just want to finish this to make sure you guys can do the problem. So very easy, guys. Very easy. You don't have to graph the whole function, but at x equal to 5, there is a vertical asymptote. So right there, x equal to 5. Okay, now check this out. On the left of 5, here's 5. On the left, the function is negative. So it's gonna go to negative infinity, like that. Okay? Because it's negative on the left of 5. And on the right of 5, the function is positive. So to the right of that vertical asymptote, this is what the function is going to do. Very easy. The sign analysis does tell you what those limits are. So if I'm finding the limit as x goes to 5 from the left, that limit is positive. That limit is negative infinity. Okay, going down from the left of 5, and on the right of 5, it's going to positive infinity. Okay, that's it. And of course, the limit doesn't exist.
Oh, I have a quick question. How did you know there was a asymptote and just not like a hole or something?
Yeah, so a hole, we'll talk about discontinuities again later on, but a hole, remember from pre-calculus, could be possible if both top and bottom are 0.
Oh, yeah, okay.
Yeah, whenever a number makes only the denominator 0, then there is a vertical asymptote. Okay?
Okay.
All right, so we'll do more of these examples tomorrow, guys. You have a good day. If you have a question, you could stay for a minute or two, ask me your question, but we're done.
Thank you.
All right, guys, have a good day.